Hello and welcome to our presentation on 3D printed propellers and their viability to small-scale hobbyists. For this project, we are using 3D printed propellers and comparing them to commercial ones. This can be measured by assessing their thrust capability. When talking about aircrafts, and when a propeller spins, it displaces air orthogonal to the direction of motion and creates thrust, which is able to propel the aircraft forward. Various parameters contribute to this, such as diameter, smoothness, and pitch. When 3D printing, smoothness is the only thing being affected. Diameter and pitch are dependent on the dimensions of the model, while smoothness is solely affected by the production quality. Because of this fact, smoothness, which is determined by layer height in our experiment, will be the only variable we are testing.
Our test objective is to compare 3D printed propellers to composite ones by varying the layer height of the model. Smaller layer heights, smallest being 0.09 millimeters, will have a smoother surface and therefore should produce less drag. The difference is in a commercial, we're able to get large quality of very variable propellers, but the shipping times would be 2 days at the lowest, and they'd be more expensive. If we 3D print them, we'd have them available within a matter of hours. They're extremely cheap, extremely available, and we can adapt them to any shape we want, even if they're not standardized.
For the test plan, the plan was to use a thrust stand to test different 3D print layer height configurations against a composite propeller at constant RPM. Parts from a Vex Robotics kit, including motors and gears, were used to mount the propellers to the test stand and spin the propeller at controlled parameters. Both the thrust in grams and print time will be recorded and compared for the composite propeller. Shipping times online are not consistent enough to be worth recording them. The measurements were done quite easily thanks to the simplicity of the Vex system. The motor is smart enough to measure the power supplied and rotations permitted digitally. By scaling the angular velocity with the ratios in the gearbox, thus the angular velocity of the propeller is known to be 3,266.67 rotations per minute. The thrust stand measures thrust in grams digitally. Thus, no calibration or special techniques were needed.
The test stand we used was available in the Design Build Fly Lab. It's a Myatech thrust stand, which is a Chinese company, and it measures thrust between 0 and 10 kilograms. The voltage measurement range and the current measurement range are as shown, but aren't used in our calculation. The motor base size doesn't matter because we have a 3D printed mount, which mounted to the Vex Robotics piece. The power input was a battery despite the specifications. Size and weight are shown.
The propeller was powered using standard equipment from a Vex Robotics competitive kit. This includes the brain, battery, motor, and various hardware. The electronics are all made with sensors built into them, so reading propeller speed was as simple as looking at the display. As for the gearbox, it was designed to allow the propeller to spin at the highest speed possible. We geared it up as much as we could until the motor struggled with outputting the torque to bring it up to speed. That was our limit. This allows us to spin the propeller at the highest possible speed this motor could produce, which was just over 3,000 RPMs, with a gear ratio of little over 16:1. Now, the 3D printer we used was a personal one of mine that I have stored in my dorm room. It is a commercially available Anycubic Cobra 2.
This is the commercial propeller we used for a baseline acid comparison to compare against our 3D printed propellers. It is made of nylon with a 7-inch diameter and a 5-inch pitch. The hole diameter is 7 millimeters with an 8 millimeter thickness. This gave us a reliable reference point for how smooth professionally manufactured props will perform against the ones we 3D printed. Our project started in mid-January by laying out a test plan and assigning roles. After getting some early feedback, we shifted focus from general thrust testing to studying how print quality affects aerodynamic performance. We finalized our direction by late March and comparing 3D printed props with a composite one, using layer height as our key variable. Over the next few weeks, we printed the props, set up the Design Build Fly thrust stand, and conducted controlled thrust tests for rough, medium, and smooth prints. By April 13th, we had wrapped up testing and began analyzing data and finishing the report. We were lucky that most equipment we needed, like the thrust stand and Vex components, was available to us for free. The only real cost came from the commercial propeller, which was $8.20. Filament costs for the 3D printing were negligible. As for the risk assessment, spinning any kind of propeller at high RPMs, especially ones made from unknown or potentially brittle materials, always carries some risk. There was a chance pieces could break off. To stay safe, we wore safety goggles and made sure no one stood in line within the propeller's rotation.
For our results, our experiment is listed in the table below. This was the first experiment that we tested. Our layer heights varied from 2.5 millimeters down to 0.09 millimeters. We recorded how long it took to print it, and our test stand recorded the thrust in grams. The RPM stayed constant through all of these. What happened was we noticed there was an error in our print design. The infill was a little bit too small than what we needed. And so what happened is it sheared and broke off during testing. This shown is an image of the 1.7 millimeter layer height propeller that broke. So we would assume that the 2.5 millimeter height would also break, which is a lower quality. What we did is we changed the infill density, raised it from its default value as high as the settings would go, which ended up being 30% infill, and changed some tweaks with the gearbox to make it more stable, and we got the following results, which we see next. Now, the print time varied because it's a little bit random how the 3D printer, how long it takes per layer. The RPM stayed the same, layer height stayed the same, but our thrust went up slightly after making the propellers more stable. Also, our composite propeller came and was shipped to us. So now we were able to test that as well. And we found that the composite one performed significantly better than the similar dimensioned 3D printed ones.
So as with any experiment, this one came with some uncertainty. The biggest issue was vibrations from the thrust stand. The stand measures thrust by reading force along a rod, and any shaking that made that reading unreliable. Another factor was the stand's accuracy. It's designed to measure up to 10 kilograms, but our forces were under 30 grams, so there was a little bit of wiggle room in between there. Without decimal resolution, our final measurements weren't super precise. Finally, like print supports or slicer settings may have slightly affected the surface finish, adding some variability beyond just the layer height. So here's what we learned. 3D printed propellers are actually a decent option for hobbyists who just need something quick or want to test ideas, but they're no match for commercial props in strength or quality. The commercial nylon one is just way stronger. Even though PLA did survive the test, it would definitely snap in a crash, unlike the nylon ones. On the positive side, our results do suggest a pretty clear trend. That lower layer height, it does improve the thrust performance. That means with a high-end printer, you might actually get close to a commercial performance. Moving forward, there are a few things we could do to improve our results. First, we'd like to use better printers, maybe ones from even this university, to hit even lower layer heights. Second, we'd run more tests with more variation to better account for error. And finally, we'd try larger propellers since bigger thrust values would be easier to measure and more meaningful for analysis.
If we were to do this experiment again, here's how we would account for our errors. The vibration being the largest problem, we would fix by using a better motor calibrated electrically. The VEX system was great because it was convenient and it allowed us to control RPM digitally from the system. But if we were to calibrate an actual motor from a power supply, we'd be able to measure the voltage provided against the RPM, and the commercial motor would create significantly less vibration. We would also use a larger control RPM and diameter because larger values of thrust based on our stand specifications would be more accurate. We'd have more propellers as well, so we'd have more iterations to quantify, because as of now, with 3 iterations, we have a linear trend, but we want to make sure that that trend is precise. And then we would try different materials, such as resin or other 3D materials.
And that concludes our presentation.
Thank you.
Thank you.